what we're going to do now is go beyond the basic concepts and to look at some subtleties. Subtleties in the design of RMI. You know, I've sort of advertised Java RMI as this wonderful abstraction that extended the state of the art in many ways. It's not just an implementation of existing ideas, it had a lot of new ideas. But it made some design decisions which are not sacrosanct, and I'm going to compare it with another RMI layer that I built as part of a system called GIPC. And I built GIPC mainly so that I could give students a framework to implement RPC. So it's an extendable framework. But when I was implementing it, I just thought I'd have some fun with the design also. Okay, try to see what if I do some what if things. That what if I change some decisions Java made? What are the consequences of it? How might I change? How might I change the implementation, the semantics, and so forth? So your assignment 3 is using RMI on your MapReduce problem. Assignment 4 is also using RMI, but on a different problem. Assignment 5 will use GIPC on the same problem assignment 4 does. Okay, and GIPC and RMI are very similar to each other. Okay, so your code will change very little. Okay, so that's going to be a very quick assignment. The reason why I want you guys to implement it using GIPC is because later you will go and change GIPC, and the changes to GIPC will be reflected in your application. So you will actually be using the changes that you make. Okay, so I'm going to use these two examples to go and illustrate some subtleties with RMI and with more method unification in general. Okay, and some of these subtleties have actually been brought out in question. So here's a table that I will also have in assignment 5 that shows the difference between the two layers, and this table will make more sense as I explain these concepts. But this is just an overview. We'll keep coming back to it, and this is something you can reference for your assignment. Okay, so I said some of the subtleties have been raised earlier. So much earlier in the class, Andrew posed a question, and I said, we'll address it later. Okay, and we're going to address it now. So we saw, Adi mentioned that, look, our remote interfaces were not extending the original interfaces. Okay, so why were they not extending? That's one question. And it has to do with typing. So we're going to really focus on Java typing. If you think you understand typing, this is going to challenge your understanding. This is going to show the limits of your understanding here. Okay. So the question that Andrew posed was, can I have the same class implement a method that has two different headers? And can it go and implement two different headers with the same implementation? Okay, so look at the two interfaces I have. I have counter. It has increment and get value. Distributed counter. It has increment and get value. Same signature, same method name, same parameters, same return values. The only difference is that one of them has the throws. In the remote, you have the throws clause. In the non-remote, we don't have the throws clause. And we are claiming that a distributed counter implements both of them. Is that even legal? It must be legal because I've shown you this code. It must work. If it's legal, what are the rules that allow it to be legal? Okay. So we want to answer the question, can a class implement two different interfaces with the same method header, same method signature, I should say, but different throws clauses? Okay. And that's one question. And I'm going to try to answer a simpler question first. We'll get to the answer question gradually.
Is the for get value in the interface counter, is that supposed to be an object? Because you said they have the same.
Oh, sorry. Okay, so it should be probably object. Okay. I don't know why I have object get value in the distributed counter. So it should be basically in int get value in both cases. Yeah, thank you.
And then also then in the distributed counter class.
Yeah, it should be int. I don't know what I had in my previous slides, whether I had int or object, but I don't know why I put object here. Okay, So yeah, I'll try to do a global substitution. Okay. So I'm going to try to answer a simpler question. Suppose counter and distributed counter were identical. Okay. That we didn't have throws remote exception there. And forget about extends remote also. Can a class implement two different interfaces with the same method signature and same throws clause? Is that legal? Okay, it doesn't make sense somehow, but the question is it legal? Okay. Okay. So as you guys said, yes, we can do this as long as each of those method headers appear in the class. Who cares? Whether they appear multiple times in the interfaces or only once in the interfaces implemented in the class. Another way to put that is an object can be typed by the class, of course, and by any of its interfaces. Okay, and the method headers in both interfaces are consistent with each other and with the class headers, so there's really no conflict here. Okay, if you go and type it using the class, you type it using any of the interfaces, we're talking of doing the same checking. Okay, so there's no problem. Okay. Okay, what about this now? This is the question I tried to ask earlier. Can distributed counter extend counter, and let's say there's no throws remote exception. So I don't have, I have now an interface extending another interface and having the same method headers in it that it's inheriting. Okay, so it's already inheriting void, increment, and get value, and it's duplicating these method headers in its own declaration also. Okay, so the question is, can an interface inherit a method with the same header and throws clause that it has in its that it itself declares? So is this legal? So yeah, like you guys said, like Andrew said, this is legal. It's like overriding in a class, except that you're not overriding. And I'll take questions later. Okay, I'll just okay. And so we go and can an interface inherit a method with the same header and throws clause? An interface has a union of the set of headers it defines and inherits. Okay, so it's a union of the set. So union set duplication, duplicates get removed in unions. Okay, so duplicates are discarded. So yes, they're stupid. In the class case, at least you could, when you override, you may change things. Whereas here you're not even changing things, but it may happen by accident. So that's fine. Okay. So why did I ask this question? I want to now ask the question that was the real fundamental question. Okay, and which is, can I have distributed counter extend? Okay, I'm still okay. So sorry, I'm not asking the question. I'm going to the previous first question that Andrew had asked. Is it legal for a class to implement two different interfaces with the same method header but different throws clauses? Okay, so why is it legal for a distributed counter to extend a distributed counter, the class to implement both counter and distributed counter, even though they have the same signature with two different headers, two different throws clauses? That seems safe, and we've built some background in our typing knowledge, and hopefully that background will help us answer the question of why this is safe. Okay, so let me just answer this in a different way than you did. So yes, indeed, the class satisfies both requirements. True. Okay, the class satisfies the requirements of counter, and it also satisfies the requirements of distributed counter, because the class is less restrictive than the counter. So anybody who's expecting a remote exception will be happy when there's no exception. Okay, because exceptions may or may not occur. But the fact that the class implements two different interfaces is not an issue. So that is an argument for saying that a distributed counter, the class, can implement either interface. The question is, do we cause any confusion by saying that it implements both interfaces? Okay? Do we cause any problem by saying that it implements two interfaces, both of which are consistent with its headers, but which are inconsistent with each other? Okay? That is the question I'm trying to ask. Well, a variable is typed by one type at a time. Okay? So it's either typed by the class or by one of the interfaces. Okay? If it's typed by the class, it knows which headers to look at. If it's typed by one interface, it looks at the headers of that interface and uses them for type checking. So if you go and type something as counter, it doesn't look for a catch. It says, oh, there's no remote exception. If you type it using distributed counter, then it looks for a remote exception. Okay, so there's no ambiguity as to whether it should go and look for a catch or not, based on how you typed it. Okay, so indeed the class satisfies the constraints of both interfaces, and it can implement them both with each other together, even though they're inconsistent with each other, because each interface is used separately. Okay, and now I come up with the Adi question. Okay. Can I make distributed counter extend counter when its header has remote exception, whereas counter's header does not have remote exception in the throws clause for the same signature? That is the question I want to get at, and is that legal? Okay, so we have now distributed counter extending not only remote but counter. This is what we really like to have. Okay, and increment in distributed counter is duplicating the increment in counter, except it's not quite duplicating. It's duplicating the signature but not the exception. So this is not so stupid. Okay, this is like overriding, if you will. Okay, so can an interface inherit a method with the same header but different throws clauses? That is the question. Okay. Okay, so last time we looked at this example with our running example, where we have a counter with two methods, and neither method says it throws any exception. And then we saw that to create a distributed counter, we had to create a distributed interface, distributed counter, which extended remote, and it duplicated the signatures in the counter interface, but the headers were different. The headers now said that the methods throw remote exceptions. Okay. And then a distributed counter implemented both the interfaces. Okay, distributed counter had the exact headers that counter has, okay, but it also said that it implemented remote exception. And we saw that was fine because a class can, the classes clause can be less restrictive than the interface clause. Okay. So one question that came about, that arose was that could we have made distributed counter extend counter? So that both counter and the proxies to counter can be unified by one type. And that raised the more fundamental question that can an interface inherit the same signature with different headers? Different headers meaning we have two different throws clauses, or we have, that's what it really means for interfaces. Okay? So can it do that? Or, and relatedly, can it override a header that it has inherited? Okay, by overriding, I mean that you have a header with the same signature but different throws clause. Okay, and we said, you know, an interface has a union of the set of headers it defines and inherits. Okay, it's a set. And if the same signature is inherited from two different interfaces with different headers, then when that interface is used to type a variable, and invoke a method on that variable, it's not clear which throws clause should be used. There's ambiguity. Okay. So then the next case is, well, and this is a little longer, this is based on Nolan's comment, that what happens if, you can certainly have the interface override the header of an inherited method. And in classes we override, so why not in interfaces too? But then you can't have the overriding method be more restrictive than the overridden method, okay, because of the way typing goes. Okay, so this is a long piece of text that we discussed in class last time, so I won't go through it again. Okay. So that's where we were last time. And why was I talking about inheritance? Well, you might want to do it, but a more fundamental reason. I'm going to say, based on our understanding of the typing, an implication can be made that you cannot invoke methods that you inherit from class object remotely. So you cannot invoke toString, hashcode, wait, notify, equals remotely. You can invoke increment and get value that you define yourself remotely, but you cannot execute methods inherited from object remotely. I'm claiming this is an implication of the answer to the previous question. Okay. So think about it and try to figure out why this implication is made from the previous conclusion. So to sort of give Leo's answer in a more long-winded way, let me pose a couple of other questions. Can I, in the interface counter, put the method Boolean equals object other object? Is that legal? Okay. And then the other question is, can I put in distributed counter, which extends remote, the method equals other object throws remote exception? Okay. Is any one of these two legal? Okay, so is this legal? And is this legal? And Leo kind of answered the question already, but let me just pose this question more specifically to you guys. So this is fine. It's consistent with signature and object. Okay. And this is not fine because the overriding header, as Leo said, cannot be more restrictive. Okay. But let's try to really understand what's going on here. When we talk of overriding, we talk of super types, right? So we talk of a class overriding a superclass's methods. A class overriding is maybe its interface methods. But do we ever talk of an interface overriding a class's methods? Okay. Is interface ever a subtype of a class? An interface can be a subtype of a type if the interface extends a type. But is an interface ever a subtype of a class? Does any interface does any interface extend object directly or indirectly? Okay, so the answer is, interfaces don't extend classes. So what's really going on here? Are we really overriding or are we not? So regardless of how a variable is typed, and this is what Adit was trying to say, the method signatures and headers of object are visible. So I can go and type a variable using any interface, and that interface could have no methods in it, or that interface could have some methods in it. You can always invoke equals on a variable typed using object. Typed using an interface. Invoking equals on a method typed using a class makes sense, right? Because every class directly or indirectly extends object. But you can, for practical reasons, always invoke the equals method on a variable, because we know that every object ultimately has that method. even though the interface doesn't have that in its explicitly, we know that every object has that method. So regardless of what interface is used to type a variable, we can invoke object methods. Okay. So object has an implicit interface essentially that is inherited by all interfaces. It doesn't have an explicit interface. I wish they had created an interface for object, okay? But Gosling didn't. But the way the implementation goes, essentially there is an implicit interface. Okay? There is some special casing in Java that allows that to happen. Okay. So and so indeed Leo was right, and indeed we cannot call object methods remotely. Okay. So we see now that we have two problems that this whole notion of checked remote exceptions has created. Objects methods cannot be called remotely. Okay, so that's one problem. That means if I have two proxies, two equivalent objects, so if my two proxies both point to objects that are equal, okay, there's no way for me to make sure that the two proxies themselves are equal to each other. Okay, you would think that if two proxies point to equal objects, then the proxies themselves should be equal to each other, but no, we can't. We can't do a remote call to determine if the two remote objects are equal to each other. So we can't really determine if that is the case. Okay, and there was another problem we saw, which had to do with the fact with reusability. We saw that property chain support could not be used to store remote objects, because property chain support needs to call methods on those objects, and if those objects are remote, then property chain support should be ready to catch remote exceptions, but it's not. So ideally, we would, if we didn't have to worry about remote exceptions, ideally, wherever an object O can be stored, we should be able to store a proxy to object O2. But we can't. Okay, just because proxies throw remote exceptions, and when we invoke methods on proxies, we have to be more ready to do more things than when we invoke methods on object. So, checked remote exceptions have the advantages, but I want to point out the cons also. Almost any design decision we make, there are pros and cons. Okay, and here are the two cons of trying to make sure that these exceptions are checked. Okay. So there's a trade-off between forcing error recovery for safe and correct programs and flexibility and reusability. And you can argue that, in today's world where security is important, we don't want bugs in programs because they can be exploited to create security issues. So it's okay for programmers to sweat more and for us to, lack some flexibility. We can define our own equals method that is different, but does with a different signature that can do the equals itself. Okay, we can't use the objects equals method. So maybe that's the right decision. Okay, but I just do want to indicate that there's a trade-off here. And to just explore this trade-off, I told you that I built GIPC, and I really wanted it to be a customizable environment. But just because I was building something on my own, I wanted to experiment with different choices and understand the consequences of them. So in RMI, the exception that is thrown when there's a distributed error is checked, as it should be, based on the checking rules. And in GIPC, I cheat. Okay, I say, well, I want reusability, I want flexibility, I want to understand what it means to call remote objects, object methods remotely. So there is a GIPC remote exception, which is in my package, and it's unchecked. Okay, and so you guys will use GIPC, and you need to be aware of this, and you need to, more importantly, be aware that we can generate a system, we can build a system that does remote method invocation, in which we have the advantages of invoking remote object methods remotely, and the advantages of reusing existing code. Okay, and this is not totally a crazy idea. Before Java was invented, there was a system called Cedar from Xerox. I mentioned Xerox to you guys last time, or in one of the previous lectures. And Xerox had built a system where you can take an existing non-distributed program and make it distributed. In GIPC, you still have to make certain things distribution aware. Okay, but they just made the whole program, the whole system. In fact, the whole operating system was distribution unaware, even though it was distributed. Okay, so it means they were not doing any remote exception. They're the ones that invented exceptions, from what I remember, Mesa and Cedar, but they didn't have the notion of checked exceptions, but they weren't forcing the Java way. So what I'm doing in GIPC is somewhat in between Cedar and Java. Okay. So in GIPC, you don't have to put throws remote exception in interfaces that have to be called remotely. Okay, and so this is legal. So does it make sense then to have even the remote interface at all? If we are not going to force our remotely called methods to have throws remote exception in their headers, in the interfaces, does it even make sense to have the notion of a predefined remote interface? That's exactly right, what Jason said. We might want to make sure that only certain methods are available remotely. So the programmer of the class, of a remote class, can make sure that the methods that have to be called remotely are put in interfaces that are remote interfaces. And an interface is remote interface if it is a remote. Okay, an interface is a remote interface if it extends remote. Okay, so the remote would still be useful. So we see now that RMI uses remote in two different ways. One, to make sure that the server class has control over what methods are called remotely. And second, to make sure that when a method is called remotely, the caller is ready to catch remote exception. Okay, there are two purposes here, and Java uses both. In in GIPC, I ignore both. Okay, certainly, and the advantage of ignoring the first one is that we can call object methods remotely. And the advantage of ignoring the second one is to not have the disadvantage that RMI has, to be able to use existing classes. Okay, because those existing classes are not implementing remote interfaces, and I want to be able to use them remotely. So I want to use property change support remotely, and I can't do that if I require property change support to have implemented a remote interface. Okay, but one can design a system where you have chosen one or both of these implications of remote. Okay, roles of remote. Okay, so again, I'm trying to just show you what the design space is, not necessarily to go and advocate for one choice over another. Okay, there's trade-offs. Okay, so let's try to go and reconcile these two facts that we have figured out in RMI. Regardless of how a variable is typed, the method signatures and headers of objects are visible. That means the equals method and the toString method and the hashcode method and the wait method are all visible when we are using a proxy. It should be possible to call all of these methods on proxies. But we also know that when you call methods on these methods on proxies, they don't go to the remote object. That means as the RMI designer has to figure out what the meaning of these methods is, what the meanings are when we are using proxies. Okay? So we need to figure out, for instance, what equals means when equals is being called on a proxy rather than on a non-proxy. Okay, for non-proxies, we have existing Java rules to tell us what equals does. Okay, equals looks up the chain to figure out an implementation of equals, and if it finds nothing else, it goes and uses objects equals, which is just equals in fact. Otherwise, it uses the method. So proxy class is not something that we implemented. It was generated by Java, so by RMI. So RMI has to somehow figure out what the proxy class is, what methods do. Okay. So our question is, what does it mean to call equals and other object methods on a proxy? Okay. And we know that in, or if you don't know, you should know that in class object, equals is defined this way. Okay. That basically if the two objects are same, then equals returns true, otherwise it returns false. That's because class object doesn't know what state you have stored in your object. And so it can't go and compare the states. So it just says that if they're both equals, then equals returns true. Okay. So the reason why string equals and list equals and vector equals do the right thing is because all these classes have overridden the object equals. Okay. So similarly, we need to somehow override the equals method meaningfully for proxies. So such an override should look at the state of the proxy on which equals is invoked, right? It's got to be state-based, otherwise it can just do what class object does. So this raises the question, what are the components of the state in a proxy? So what state does a proxy really have? And that's an interesting question in its own right. Forget about equals. To understand how proxies work, one might want to know what state is really stored there. Okay? So let's go and try to figure out the answer to this question. So the answer to the question depends on the following question. What information is needed to forward a call to a proxy? That's what a proxy's job is. Given a method call, it has to go and forward it to the remote object. So what information is needed to do the forwarding, and that must be the information stored in the proxy. Okay. And just to sort of refresh your mind on how proxies are used and what state might be stored, let me remind you how proxies are used in clients and in servers. So a client code just goes to a name server and gets a name server first, and then looks up a proxy from the name server. Okay, and when it does the lookup, it goes and gives a name, external name of the proxy, of the object. Okay, and then it can do something like counter.increment minus 25. And we need to know what information must have been stored in counter to make sure that the increment goes remotely. That's what we need to find out. Okay, so it must be some state that is a function of the name of the external object, right? Because we did a lookup of that name from a particular registry. So what information may be associated with that name can be maybe derived by looking at the server code. Okay, the server code creates some remote object, creates an object, local object, exports it on a port. If there's no port, it says 0. If the port is default, it's 0. And then it goes and associates that that object with a name. Okay, so based on these two pieces of code and what we've seen before in our various lectures, let us now try to answer the question, what information is needed to forward a call to a proxy? So assuming there are many ways to implement this thing, okay, like you guys, and that's probably the reason why you took so much time. Okay, but let's go and assume implementation on a Unix-based data port. Okay, that means we have a port number, and we have a host associated with this. Okay, and that's not how Xerox did it, for instance. So this is just on a Unix-based systems, and today's modern systems all tend to be Unix-based. So if we assume that, then we need to store the host and port ID. Okay, that's part of the persistent. So some information, like I said, is call specific. That's not what I meant when I said that what information does the proxy need to forward the call. It will certainly forward the call specific data like call ID and parameters, but there's also call independent data that it needs to store that it forwards. Okay, and that is something that the caller doesn't supply each time. So that is inherently in the proxy, and it's got the host and port number. Then it has to somehow identify the signature and the interface. That means it must know what interfaces that remote object has. Okay. Once an proxy is generated, The client can type it using any one of the legal interfaces. Okay, the proxy should be possible to use the same proxy with different interfaces too. So it must have all the interfaces that the remote object can execute. It must have knowledge of them. Okay, that means in the code that the client has, that interface must exist. Okay, that makes sense, right? The class doesn't need to exist. Okay, often you don't want the class to exist because you don't want the implementation to be visible to the client, to the caller. But the interfaces must exist. So it has to know what the interfaces are. Okay, it needs to identify somehow the interfaces. Okay, and from that it can then go and send an identification of the method called. And sorry, I said this in opposite order. Plus, it must also send the external name. Okay, there may be multiple objects in the server, in the calling side, that all implement the same set of interfaces. So it must identify which object, which instance also. Okay, so I said this in reverse order. Host and Unix port number, the object, and then which interface and which method in the object. Okay. So this has, you get an idea of what's going on underneath through this. You get an idea of how you might implement equals also. But I'd like to say the following, that the information needed to generate a proxy for an exported object is the information needed to forward calls to the exported object. Okay, again, when I say information needed to forward calls, I mean the information that's always sent, that is call independent. Okay, so you can say that, look, if the state of the object is what is the persistent state of the object, so the persistent state of the object is what is needed to generate the object. Right? Okay, so the same set of information, host, port ID, interfaces, given these three pieces of information, I can generate a proxy from that, because then I can correctly initialize the state. Okay. So the implication of this is that the proxy can be generated from the host, Unix port number, an external name of an object bound to the name, making these assumptions about the implementation. Okay. That in turn has an important design implication, which I've used in GIPC. Okay, so I said in GIPC I cheat by not requiring the remote exception to be checked, and I also cheat by not having a name server. Okay, so you don't need to have a name server to get proxies to remote objects. Okay, so far you said, oh, if I have a remote server, name server, we can do a rebind, export, and lookup, and get proxies. Yes, that's one way to get proxies. And that is one way to go and get the information needed to generate a proxy. But I can do it more directly. So I can, rather than going, we realize that proxies are instances of objects classes whose names we don't know. So we decided that we needed a factory. Our name server was a remote factory. So it served the purpose of a factory. It happened to also be remote. All I need is a factory. And the factory need not be remote, it can be a local factory that is supplied with this information. Remember, a factory is given some information about the instance. Given that information, it goes and gives you a copy, gives you the instance. So I can give a local factory these three pieces of information and get a proxy for an object. I don't have to go to a remote factory. I don't need a name server. A name server has certain advantages, but if all I need is a proxy, I can be without a remote name server. Okay. So, to explain this in slow motion, let's go and see how proxies are created again. We've seen this before in RMI, and then I'll contrast the proxy creation. When I talk of GIPC, I'll contrast the GIPC implementation with the RMI implementation. Okay. So in RMI, there are three parties: the caller process, the callee process, and the RMI registry process. Okay. There's this registry type which has rebind and lookup. Callee does rebind, caller does lookup. Okay. So the binding of names will still have to be done in GIPC by the callee, right? That they have the control. And then we have a way to get access to a registry, a mapping, and there's an RMI registry process that creates a registry object, and that can be a separate process, as you will see in assignment 4. But in assignment 3, you will in fact have the RMI registry process part of the callee process. Okay, so when the RMI registry is a separate process, both the caller and callee need to get access to a remote registry through proxies. Okay, and in your assignment 3, the callee needn't do a get registry; it can create the registry by just becoming itself the RMI registry process. Okay, that's the situation in RMI. And before you rebind an object, if you want a proxy, you do an export of the object, and that's where the unicast remote object comes in. Okay, so Randy, this is how RMI works. Okay, this is what you need to know in one slide. Okay, and go through my slides and try to understand this in depth. Okay, so the callee goes and exports the object. In GIPC, in RMI registry was an optional process that was part of the RMI API. In GIPC, RMI registry is not part of the GIPC API. You can build a registry object just like any other server. Okay, so you can implement your own registry object and registry process that is like a name server, but you don't need to have it as part of the API. The API is skinnier. Okay, you don't have RMI registry, you have GIPC registry. By the way, I did all these things using different interfaces. Then I decided that I was going to make this mimic as much as possible RMI, so that your existing code can be transported from RMI to GIPC with no modification to the server classes and very little to the server remote classes and very little modification to the clients and servers. So I've tried to make things very similar to RMI registry. Okay, to RMI. So you have GIPC registry rather than registry. Okay. Your lookup is different now. Your lookup is going to a local factory. Okay, so it needs to give the local factory enough information to create the proxy. The local factory, in RMI, you went to a remote factory that already had some information about a name. Here, you are telling it exactly which interfaces to associate with the proxy. So what you do is you give it one class, and all the types, that class could be a class or an interface. All super types of the class that are interfaces are gone and stored with the proxy. So it looks at all the super types of that particular type, and those that are interfaces are bound to the proxy. So those are the methods. Those are the types that define the methods that can be called remotely. Okay. Callee will still go and do a rebind to associate an internal address with an external name. Okay. Oh, by the way, so the lookup also takes a name. So we need to make sure that the bind and the lookup correspond to each other. So the name is there in both cases. Okay. We have a registry. Okay, which stores some of the persistent state of a proxy. So the callee. So there's no RMI registry. So the registry is creation not done by RMI registry. A callee will create a registry that is local to it, where it will go and invoke the rebind operation on that registry. Okay, so both the rebind and the lookup have to be done on certain registries, and the question is, where do the registries come from? So they are not the same object. So the callee has a local address space that goes and associates a name with the internal address. So it goes and creates a registry and associates these two and makes the association through rebind. Caller also calls a static method on GIPC registry, and it gets a different object now. It gets a local factory, and to the local factory it goes and says, here's the host, here's the port that I want you to connect to. Okay, so this is the information that is needed to generate the proxy. So let's go and be clear here. It's like I said, I've tried to keep this isomorphic to RMI, so things become a little bit more convoluted than they need to be. Remember, I need to do a lookup. If I create a proxy, I need the name of the remote object, I need the interfaces, I need the host, I need the port number. Okay, this is done in 2 stages in GIPC. First, I get a registry, giving it the host and port number. So now I've got the host and port number in the registry. Then from that registry, to that registry, I go and give them name and interfaces. So between the registry and the lookup call, I have got all the information that I need to create the proxy. Okay, and again, this 2-step process happens mainly because you're going to have multiple lookups done on for the same connection. So that makes sense, and it also is isomorphic to what RMI does. Okay, there's an extra argument. So get registry returns local factory for callee, not a proxy for remote factory. This is important. Okay, it's just creating a local factory that's associated with a particular data port connection to the remote server. And there's an extra argument that you don't have to worry about in terms of concepts, but in RMI, it's possible to figure out what host a call came from. I haven't told you how, but you can become distribution aware. So when a call occurs, you can try to figure out who the caller is. I want to know, in GIPC, there can be multiple processes on a host, so that's not enough information. So every client, every caller has a string name that they supply. And this name is sent on each call. So this extra argument is around to go and identify who the caller is if you need to know. Okay. So caller string accessible to callee. And the callee doesn't do a get registry. The callee always does a create registry because it's always local. There is no unicast remote object. There is no export object. And there is no call to export object. Okay. So here's another way to get a proxy with the same information, but in a different way, by making different design decisions. Okay. So some things in the API remain the same as in RMI, though they behave differently. But some arguments, if there's a rebind in registry in the RMI case, there's a rebind with the same arguments also in GIPC. Okay. There's create registry in RMI, there's still create registry in GIPC. Okay. There's a get registry in RMI with a string argument that gives the name of the object and name of the host, and an int argument that gives a port. Same thing in GIPC. Okay. There's a lookup in RMI that takes an object name. There's a lookup in GIPC that takes an object name. Okay, these are the similarities. Here are the differences. In the lookup also tells you what interfaces to use to create the proxy. In RMI, that information is derived. The export object went and associated, when you did export object, the system looks up the interfaces that are remote and goes and associates those interfaces with the proxy. Okay, implicitly, you didn't have to do that. Here we do it explicitly. Okay, and this extra string argument to identify the caller, which I think is just convenient, which has nothing to do with a remote or a local registry. Okay, and there is no notion of exporting object. Exporting object is done so that I can create a proxy in the server, in the caller callee, send it to the name server, from which it can be retrieved by the callee. Since the callee is creating the registry, the proxy itself, it doesn't need a remote registry, so we don't need to have export object. Okay, it's basically just a it just doesn't apply. Okay, so So let's go in again, if this is a little confusing because it's different. Even in RMI, I can have the remote registry be in the local server process. That's what is happening in assignment 3. So in that sense, this is not so radical. Okay. However, and let's just go and test how much you've absorbed in all that I've said. The lookups have different reliability and efficiency in GIPC and RMI. So RMI can simulate GIPC by just having the server have the registry in its process. But I'm claiming the lookups have different performance and different reliability in the two cases, even when in RMI the registry is local, in the server is local. So why is that? Okay, so the lookups have different reliability and efficiency. In GIPC, lookups are local, so no round trip. Okay. Proxy can be created before callee object. So there's no intermediate mediating server. So the callee object may not even exist, as Chris pointed out. So unlike Java RMI, target object name may be invalid. Okay, so there's no way to ensure that the name you gave is, so the object that you want may exist at the remote end, but you may have the wrong name for it. Okay, it just creates a proxy from the information given. Whereas, as Chris mentioned, in the RMI case, you have to fetch a proxy for an object that's already been registered. If the registry didn't occur, the fetch would fail, so you would know at that point that there is no object, not at calling time. And so when you have an unbound proxy object that's equivalent to a null pointer exception in the local case, and you essentially can get a null pointer exception in GIPC, but you wouldn't get it in RMI. Okay, that's a trade-off. Okay, because you also have to make a round trip. You have to go and do a little bit of handshaking before you make a call. Okay, so why did I do this in GIPC? To be different, just to sort of see things differently, but also, as it turns out, I distinguish between data ports and remote assignment ports and remote procedure call ports. In RMI, the data port underneath is totally hidden from you. In GIPC, you can pass on the same data port. On the same port, you can send messages, data, or you can send procedure calls. And in data ports, the same philosophy is used as GIPC, that you can try to connect to a host, to a port that doesn't exist at the other end, and you'll get a connection refused or connection not enabled message, which is equivalent to getting a proxy that's unbound. Okay? So it's consistent with that. And like I said, you can always create your own name server on top of GIPC to go and have RMI semantics. And more fundamentally, it's not one system versus the other. It's more what is your design space? That this is not the way it had to be. Okay, this is not gospel. And B, what are the design trade-offs in choosing one point over the other, which is what I want to emphasize. Again, by giving you two real implementations, I show you some of the trade-offs. Okay. So you guys have been using RMI registry, of course, and as a part of RMI. And I mentioned last time that GIPC registry is a lot like RMI registry, and GIPC is a lot like RMI with a few differences. And we talked about those differences last time. But one difference that was confusing, UG came to me after class and asked me this question, and I can see why he was confused because of the way things are named. The confusion had to do with GETREGISTRY. Okay, so the GETREGISTRY call exists in both RMI and GIPC, and I mentioned last time. So that's something that only the caller executes in GIPC. The callee doesn't, okay, because we don't have a server. So one confusing thing was what does, is GETREGISTRY, does it involve any remote communication? So the way GETREGISTRY is named, I named it the same way RMI did so that you could just easily change your code. The semantics could be, which is what UG thought they were, that you go to the remote server and get the whole state of the registry from there and cache it locally. Okay, that's not what happens. So GETREGISTRY does not cache the value. It creates a local factory. So registry is a factory. GETREGISTRY just returns a local factory rather than a remote factory. And all it does is create a binding. It's going to use underneath a data port for communication. So it just goes and creates a data port and stores the host and port number associated with that port. Okay, so that's just a local data structure. So that when you go in and later get a proxy, you know the host port, host and port, and you know from the proxy call, which is no longer visible. The proxy call takes the interface and name, so you have enough information to create the proxy. Okay. So the differences between GIPC and RMI so far, we'll see more, are that RMI stresses reliability through checked remote exceptions and client proxy fetch. So when you do a proxy fetch from a client in RMI, you know that the other object exists because you went to a remote place and got the proxy from there. Whereas in GIPC, you just made a local call. And like I said, the local call just stored the host and port number. So it's only when you create the proxy at that time, it's only when you make a call to the proxy that you will figure out there's something wrong. Okay. So GIPC stresses performance. You don't have to make a remote call to create a proxy. And it stresses flexibility because we don't have checked remote exceptions. And so we can reuse existing code, and we can invoke methods in class object. We can invoke the toString equals hash code methods, etc. remotely. Okay. So let's talk about invoking object methods remotely. You know, what does that really mean, and to see that through examples. Okay. So what it means is that proxy methods are generated for object methods, and there's an option to disable the invocation also selectively. And why do that? Like I said last time, I just wanted to experiment with RMI, with my own RMI, and see what the consequences are of invoking the methods remotely. And I thought, invoking equals and toString and hash code remotely was a great idea till I started debugging code. If you ever debug code and you select an object, it'll go and invoke the toString method on the object to display its value in the debugger. So every time you're debugging a remote object or a proxy, it makes a remote call. And that can really slow things down. Okay? So that's why I allow disabling. Okay? And here's the example to really understand what the effect of invoking remote calls is. Okay, maybe toString is not a nice method to call remotely, but equals could be. Okay, so let's try to understand equals in particular, and we'll understand a little bit about toString also. Okay, so I'm going to use the same counter I used earlier, except that now I have a toString also, and you guys get to see from this toString how the object toString works. I could have just done super dot. So what I'm doing here is using the object toString and as a prefix of the actual toString, and the suffix is the value of the counter. Okay, so you can get to know which counter we are talking about, and you get to see how objects toString works because I've reproduced the code that class object probably has. Okay, and let's look at equals. Okay, so equals, as you know, is a method inherited from class object, and it takes as an argument an object. If you're going to compare a counter with another object, you need to first check if the other object is a counter. If it's not, we know they're not equal. Okay. Otherwise, we go and cast the object to a counter and get its value and compare the values. Okay, so this is what the equals is in the regular counter. Now, we'd like to convert this counter into a distributed counter, and we'd like to have maybe a different equals that allows us to go and compare a remote object, a local object, with a proxy for it. Okay, we know we can't call an equals on a proxy that takes a remote object as an argument, but we can invoke equals on a remote object that takes a proxy as an argument. Okay, so or can we? So let's go and see. I kind of hinted that we can, but think about this, and this is when you guys will have to really use your imagination. So can we compare local counter with remote proxy, and if so, how? Okay, so this one compares a counter with a local counter. Can I compare a local counter with a remote proxy? Okay, so I have a proxy to a counter, and I'd like to go and compare this local counter with that proxy. And I'm willing to rewrite equals. Okay, so the question is, can we do this? And if so, how? And I'm hinting that we can. Okay, so that's the question. Okay, so we're going to basically create a distributed counter that extends a counter, and like I said, the interface is distributed counter, the interface, which has got the same headers as counter, except that it's got the throws clause in it. So we go and say, if it is not an instance of distributed counter, that means it's not a proxy, we'll do whatever our superclass does. And a superclass will go and check if it's an object or a counter, and will go and appropriately change them, which is correct, make the comparison. Otherwise, it's very symmetric to what we did before. We go and now cast the object to a distributed counter. And since we are casting it to a distributed counter, we go and catch the remote exception and handle the remote case. And so it's this just shows you how a remote call differs from a local call. Okay. So the only difference is that we must cast other object differently, and as a result also catch the exception. Okay, so this requires much more thought, and this is going to test your understanding of what's happening in RMI. So what we are doing here is creating two distributed counters. Okay, counter 1 and counter 2, and we are exporting both of them. So we've got proxies of both of them, and then we are binding both of them. And these two objects are bound to two different names. One is the named constant counter 1, the other is the named constant counter 2. Okay, so we have two counters, distributed counters, and they both are initially 0. They have the value 0. We have not done any operation on these counters, so they're both initialized to 0. And we're going to now get back. We are the server, but we can get back a proxy that we sent to the server, to the name server. So I go and look up counter 1, and since that's a remote object, I get back. Since what I sent was a distributed counter, I get back a distributed counter. Okay, so now I have a proxy to an object that exists in my address space. Okay, and now I'm going to do a bunch of equals. Is counter 1 equals to counter 2? Okay, you've seen the code of counter 1, and you've seen the whole code. So will counter 1 be equal to counter 2? Will counter 1 equal proxy 1? And this is something you can't figure out right now, but you can put some constraints on what proxy 1 will print out to. So what are those constraints? And is proxy 1 equal to counter 1? Okay. So think about this now. So the output is, as you guys said, counter 1 equals counter 2. The equals method in class a counter is called here. Counter 1 equals proxy 1. That's because of the extra code we wrote for distributed counter. Printing proxy 1 does not invoke the toString method of a counter. Okay, because proxy has a different class than counter, and that class is not generated by us, so our toString is not being called. Okay, so something is being called here, and that gives you the state of the proxy. So you understand what a proxy really points to by seeing what's printed out here. And proxy 1 equals counter 1, false, because proxies, the equals method is called in the proxy class, and that proxy class is not forwarding the equals anyway, so it has no idea what the state of the remote object is. So it says false. Okay, and then the question is, will it always say false, and will it always say true? So to understand that, let's go and look at the client code now, okay, which is more complicated. So we can correctly compare a local counter with a proxy or another local counter because of proxy get value. Okay, so because the get value is being forwarded to the proxy, we can compare the local counter with the proxy. And of course, we can compare local counter with another local counter because get value, the local get value is called. Okay, but we can't do the other way around, which is unintuitive, that I can't compare, I can't say equals proxy equals counter, and if I mean I can say that, but the result is different from saying counter equals proxy. Okay, that's because we are not forwarding the calls. So now let's go and look at the client to understand more complicated semantics. Okay, so this time we have those two objects registered, and I'm going to get first a reference to the registry. Then I'm going to get two proxies to counter 1. Okay, I do two lookups for the same counter, counter 1. Okay, and then I create another proxy, which is counter 2, for the other object counter that was registered. Okay, so remember, counter 1 and counter 2 are equal in the server. Okay, but they're different objects with different names. And I've gone and done a lookup twice on the same object, and once on a different object that's equal to the first object. Okay. So what do you expect to happen here? Is counter 1 2 equal to counter 1 1, you think? Is counter 1 2 equal to counter 1 1, you think? They both reference the same object. Is counter 1 1 equal to counter 2? They reference different objects, but they have the same value. They are both themselves equal to each other. And what do we think will happen when we print counter 1 2? Are we going to get the toString method of distributed counter invoked? Okay. So I've kind of answered these questions previously, but some of them I haven't. So think about this now. Our counter 1 2 is not equal to counter 1 1, because whenever we do a lookup, we get a copy of the object in the RMI registry, and two copies are not the same object. This is what happens in RMI. Okay, and counter 1 2 equals counter 1 1. Yes, because the proxy class overrides the method in class object, and both proxies have to do the same thing, direct the calls to the same remote object on the server end. So so the states are equal, and the equals method exploits that and returns true. And because equals is not called remotely, equals is called locally, it's in the proxy has no idea what the state of the remote object is. The state is not cached. Okay, so last time Ifan thought that maybe the state is cached. It's not cached. Caching creates all kinds of problems that you guys will face when you go and implement future assignments about how to keep the caches consistent. That's going to be the next challenge. So that returns false. And then you see this print line, and this gives you, if you're confused about what the state of a proxy is, this printing out of the proxy will give you an idea what the state is. And at this point, it'll be useful to go and see what the state of the proxy. So we created also in the server a proxy to the same object, and we created a proxy in the client also to counter 1. So it'll be good to go and compare the two proxies in the two classes, server and client. Okay, so proxy equal overrides equals and is invoked locally. So if a proxy is equal to another proxy, if they point to the same object. So here I'm printing out so both of these are printouts of proxies to the same object. In one case, the proxy is in the server. In the other case, the proxy is in the client. And so I've basically taken the two printouts and put them next to each other. And so you can see the server printed state and the client printed proxy state. And you see that even though these two proxies exist in two different processes, what is printed out is identical. Okay, they both begin with 152.23, and with 432, and you can assume that everything in between is the same also. That does show you that two proxies with the same object, at least their two strings have the same printout, which must also indicate that the states are the same, and which makes logical sense because they point to the same object. And I said earlier that host and port are kept in a proxy. So we need information to get to the host and port, and it can be a reference to the host and port. And what you're seeing here is 152.23, some endpoint information, and that happens to be a pointer to the data port created to talk to that host. Okay, so that is a data point. That is a that's an indication of the server endpoint, basically, that they both refer to. So each object is exported from a particular data connection, and that data connection has a name, and that name is the endpoint. Okay, and then the object IDs are not the name of the object, which is what we need, because the name is what's registered in the registry, but some reference to the name. So rather than having a string, you can have a number that is derived from the string. It could be some guaranteed. It's just a unique ID. It could be derived in many different ways. Okay, and you see the two IDs are the same also. Okay, so that's what's happening. So now you understand how RMI is working, and the reason it's working this way is because the methods are not forwarded remotely. Okay, so interface. I also said there's information about the interface in the proxy, and that information is not printed here, but we have to know also which interfaces it refers to, so that we can go and take a method call and translate that into a method call ID. Okay, and we have about 1 minute, so let's just finish this example, and let's go and see what happens in the GIPC case with identical situation. Okay, so in GIPC, local calls are forwarded. I mean, the object calls are forwarded. I've done the same thing, and I've created a proxy to an object that is local. And what I get is, you get to see all the things that were not happening earlier. You get to see that counter 1 equals counter 2. That's true. That occurred earlier too. The same code is executed. But some of the things that did not occur earlier are occurring now. Counter 1 equals proxy 1 occurred before. It was true before. It's true now also. But now we are not getting, when we print out the proxy, we don't get a state. We invoke the toString method. The toString method is invoked on the remote object, not on the proxy. The remote objects, the toString we defined in that class, which was the hex string plus the value, is printed out. So we don't get to see the proxy state, we get to see the remote object state. Okay? And because we are calling the equals method, because equals method is being forwarded, proxy 1 equals proxy counter 1. Okay? But proxy 1 will go and call the equals method in the remote object, and that will go and check whether that will go and check its value against counter 1 and find it to be true. Okay? So you see different semantics because the call is being forwarded. Okay? And with the client, we can see what's happening there. So you might think that counter 1, 2 should be. So let's go and see what happened and try to understand. So this might be unintuitive to you. Counter 1, 2 is equal to counter 1, 1. That's true. They are both proxies to the same object. They are the result of two different lookups, but the lookups are local, and both lookups are the same argument, right? They both take. Remember, now this is a local lookup, so it takes a class and a name, okay, because the proxy is being generated locally, and they both happen to be proxies that are instances of the same class and have the same name. So what GIPC does is say, hey, I know what I gave last time as the object. So if you're going to do another lookup, I'll just return to you the same object. There's no reason for you to go and get another object. Okay. So you in fact get the same proxy each time you do a lookup with the same arguments. Okay, you get so that's why that is true. The equals is true, and the other being true is follows from what we said earlier, that since the equals methods are being forwarded, we go and see that they're equal, that counter 1 is equal to counter 1 2, of course, but that determination is made by making remote calls, not by making local calls. And counter 1 is equal to counter 1 2, counter 2, because the remote calls are made, and the remote calls determine that the two remote objects are the same, so you get the value to be true. Okay, and again you get to print out the toString of the actual object, remote object, and not the proxy. Okay, so it's 4:30. Sorry. So two lookups for the same arguments return the same rather than equal proxies. That's the point I was making. Okay, do you have a question? Okay. Okay, good. So we'll continue from here next time. Well, actually, let's look at this also. So you can see that we saw earlier, but let me just finish this up. That again, the two strings are the same, as was the case in RMI case, but the two strings are the same for different reasons. Now the two strings are the same because the two remotely pointed objects are the same, not because two proxies point to the same remote object. Okay, so that's why they're the same. Okay, so you know the basic API for RMI, and you know enough to make things work, but maybe not enough to understand what's going on underneath. Okay, and you sometimes do need to know what's going on underneath to make things work in certain situations. So last time what we looked at was, what happens when you try to invoke object methods on proxies. Okay, and we saw that in RMI those methods have to be executed locally, but in GIPC they can be executed remotely. Okay. And another issue is threads. I've kept saying that concurrent processing and distributed processing go together, and for various reasons, sometimes you do distributed processing to get more parallelism than you can get on one computer, and also to make responsive and scalable distributed programs, you need to have multiple threads. Okay. And the picture here shows that there are two processes that are communicating with each other, and they do inter-process communication, and within each process we have threads also. Okay. So one question, whenever somebody does work for you, they hide things from you. They make it that's why it's higher level abstraction. They hide things from you, but sometimes at least they hide them to the extent that you don't have to go and implement those things. But sometimes you need to know what the system is doing underneath to program properly. Okay. So one thing that's hidden from you is the threads that execute your remote calls. Okay, so a remote call involves a caller that invokes a method on a remote process. Right? We know which thread is invoking that call in the caller because you invoked that call, you as a programmer, so you should know what thread was executing it. But the remote call is executed by the system, and we may or may not know what thread is executing those remote calls in the callee. Okay. And I say we may or may not know because in some RPC systems we do know. Okay. So that's the question, which threads execute a remote procedure method in the callee. Okay. And when the system is lower level, like Sun RPC, we do know which thread is going to execute these calls. Okay, so if you may remember, you probably don't remember, but let me remind you that in Sun RPC, the callee goes and registers a bunch of procedure calls, basically connects a procedure address to a procedure ID that can be used remotely. It does that. Here we see only one register RPC, but you can do multiple register RPCs, and then it calls a library routine called SVC run. Okay, SVC run is provided by the system, but the callee executes it. Okay, and what does the SVC run do? It basically is a use. So you give it a thread. Okay, there's a thread that's executing it, and that goes through and reads from the network. Okay, looks for messages. Whenever the message comes in, it goes and dispatches the message to the right call, reads the next message, and so forth. Okay, such a thing is often called an event loop. Okay, that there's a bunch of events that are being serviced by this particular loop, and each servicing of the event, bunch of events essentially being consumed. Okay, from some external channel. So this is a producer-consumer problem, and what we are doing is making a single consumer that goes and processes messages from multiple potential producers. Okay, and this event loop is something that you didn't see in RMI, but that's a concept that used to exist. You didn't see it in RMI, but this is a concept that existed in Sun RPC, and it still exists in modern systems. Okay, so you guys have also been, when you did those of you who did 401 with me, we went through this in depth. But even in this class, we talked about the AWT thread. Okay, you can have 10 windows in a process, and you can have them all be all have different buttons, but all of these buttons all input events and all paint events on all the windows created by a particular process are serviced by one thread. That's the AWT thread, and it goes through a queue similarly and processes them one by one by one. Okay, so this event loop concept is quite common even today. Okay, so in Sun RPC, our main thread, or the thread that did execute SVC run, which typically is the main thread, is the one that's executing all the called procedures. Okay, with RMI and GIPC, we don't know which threads are going to execute. And how do we know that? We've seen this before. Okay, we saw that our main method went and created objects, exported them, bound them, and then ended. Okay, there was no SVC run here. Also, before making all these calls, the main did not go and tell the system, here's a thread to execute remote calls. And we saw that this particular program that executed the main method may or may not finish when the main method finishes. Okay, so no thread was offered to RMI or GIPC for servicing remote calls in our program, and the main thread does terminate. We see that. We in fact see that if you look at the debugger, there's no main thread left. But the program remains, and way back we saw that this had to do with exporting an object. When you exported an object, the system underneath did something. It must have created some new threads. And these are the threads that must have created one or more threads. We don't know. Okay, and that is what caused that. And these threads must be the ones that are executing remote calls. Okay. So if a process creates a proxy, it does not terminate when its main method finishes. Okay, and this is very analogous again to the AWT situation. In the AWT situation, if a process creates a frame but does not make it visible, when the main method finishes, the process finishes. But if it made it visible, then the AWT thread is created, and it's around to service all input events. And so the main method can finish, and yet your program is running. It's a similar situation in RMI. Okay, and there we know it's one thread. In RMI, who knows whether it's one thread or multiple threads, and that's what we want to get into. Okay, so proxy creation results in one or more system threads servicing RPC calls, just as frame being made visible results in one AWT thread. Okay, so let's go and talk about this. I keep saying sometimes one thread, I sometimes say multiple threads, and who knows what RMI really does. I honestly don't quite know what RMI does. And we'll see why. We'll go and try to investigate what RMI does through experiments. But let's go and have a discussion as to the pros and cons of not the pros and cons, just pros and cons, but what are some choices? Okay, so I said the system is making some decisions. Let's put on a hat as system designers, the system designer hats, and try to figure out if we were designing RMI, what would we do automatically for our clients? Okay, what kind of policies can we dream up, and if there's more than one interesting policy, then there must be some pros and cons. So let's discuss this. Okay, so we've got to most of the issues in our discussion. So one issue is static versus dynamic, and there's degrees of dynamicism. So we can have a thread pool with a static number of threads. So the thread creation will not be part of the remote servicing call time. Okay, so when a call is made, we don't go and ever create a new thread at that time. So that's good. And what's a pool? It's a set of threads that consume jobs from a shared buffer of jobs. Okay, so a thread pool is really, like I said, a producer-consumer problem where somebody, there are jobs being put in that queue, and a thread pool is a bunch of consumers that go and consume those jobs. Okay. And there's some incoming dispatcher that gets calls from the remote network, and it goes and puts these calls in the queue. Doesn't block itself. Okay, when you do assignment 4, 5, 6, you'll actually see this happening in depth. And so we can have a thread pool, and with static number of threads, and we can have the number of threads dynamic, which allows the system to adapt to call volume. Okay, so that's good, and reduces blocking. So blocking is something else that we should mention. So we can have a new thread per call or a thread pool whose size varies. Okay, so we can use the word dynamic for both. In either case, there would be a per call cost. There would be a cost that occur from either each call or some calls. Okay. And then when there's a pool, you can think about, is it per connection or is it shared? So imagine that there's 3 different, we know that underneath RMI, GIPC, and most systems have a data connection to the client. Okay, so there may be five callers which are 5 different processes, all making remote calls to a particular callee process. And the question is, should you allocate the threads pool? Should you have a thread pool per calling process, or a shared thread pool? Okay, so that's yet another issue to discuss, and there's pros and cons. So let's discuss that. So this, in general, this is a this is a more general question, that when there's a bunch of resources to be shared, do you have dedicated per user of the resource, or do you have it like that, or do you have it shared? So when you have shared, there's better utilization, which is what you guys are getting at. So here you've gone and I've given him 8 threads, but he's just using 2, and he needs 10, and those unused resources are not being used by him. Okay, so that's better utilization, but the flip side is that that somebody may hog the resources too, which I didn't get to mention in the previous slide. That the person who uses more doesn't get penalized for doing so, and sometimes you do want to penalize users that consume more resources than they should. Okay, so the next question is, should the number of threads be in a pool be small or large? Okay, so that's sort of, in the one extreme case is that we have only 1 thread, or we could have 3 threads, or we could have 1,000 threads. Okay, so should we have a thread pool size be, assuming we are using thread pools, for the pure dynamic policy, when we're going to create a new thread per call, we have no decisions to make. Every time a call comes in, we create a new thread. Okay. Now we got a pool. You got to figure out what size of the pool should be, and that can be dynamic or static. And assuming it's static, should it be small versus or large? And then the question again becomes, what are the pros and cons? Okay. So let's discuss that. So making number of thread low increases utilization. We know there's no wasted threads, okay, and we haven't used any resources. And you guys have mentioned blocking, which I'm very happy about, because blocking is a very big deal here. And making number of pool threads high or creating a thread per call allows more use of concurrent processing and reduces blocking. Okay, so dynamic reduces blocking, as we talked earlier. And when you have a static policy, then having a large number of threads also reduces blocking and uses more concurrent processing. Okay, so blocking can lead to wasted time, okay, as was hinted by David, and it can lead to deadlocks. Okay, so teaching a distributed course without talking about deadlocks, actually teaching a concurrency operating system without talking about deadlocks, you have to talk about these. So let's try to figure out what deadlock is. Okay, a little bit more formally than you might know informally. So whenever you talk of deadlocks, you also talk of starvation as in the same breath almost. So let's go and talk about the difference between starvation and deadlock. And the word starvation has already been used earlier in the course. And we never gave a definition for it. We kind of informally, we used the term, and so we informally understood what it meant. So let's go and have not a mathematical definition, but at least a definition of these two terms. So starvation and deadlock. So we say that a particular thread T is starved if it's not, you guys talked about executing. In general, you're trying to get some resource. Okay, you're trying to get access to a file. You're trying to get access to a shared, a synchronized method. So thread T never gets the resource it needs, while threads that requires a resource after it do. Okay, and the resource exists. It's not as though the resource doesn't exist, and it is repeatedly accessed and released, but T never gets it ever. It's not that it's delayed by 10 seconds or 20 seconds. It didn't get it when it should have got. It just never gets it. Okay, so if you want to ever have to prove starvation to see that, look, here's a sequence of events that will never allow this thread to get that resource. Okay, and we saw that in monitors. So here's a thread that went into a monitor and decided to wait because the condition to proceed was not right. And then the condition to proceed did occur, and it was notified. And after being notified, it has to get access again to the monitor. So we could put it in an urgent queue, or we could put that in the entry queue. If you put it in the entry queue, it goes behind other threads that came later to access the resource, and those threads might go and make the condition to proceed false for it. So it'll go back to waiting, and this can happen an infinite number of times, and it can never get that resource. Okay, that is exactly why we went and got to put an urgent queue saying we'll give the ones who have been waiting before higher priority. Okay, and deadlock is always among a group of processes, and each thread in the group is waiting for one or more members of G to take some action. Okay, so one is enough. And so then the question becomes, you guys all, and I'm very happy about this, that in the context of remote procedure calls, you all think of blocking. And let's think about how, and I kept telling you that, we need to know what the thread policy is in certain cases. Even though we don't want to know about what's happening underneath, we sometimes need to know what's happening underneath in certain applications. And I'm going to claim now that if we want to prevent deadlock in a distributed program, we sometimes need to know what the underlying thread policy is. Policy is for executing remote calls in threads. Okay, so think about this now, that try to think of a thread pool policy that might lead to deadlocks, while another thread pool policy may not for the same program. And the hint I'm giving you is think of some remote observable object, okay, where there's not just calls being made by one process and another process. There's calls are being made in the other direction too. And that happens with the observer pattern, right? You make a call, you get notified, and then you can make another call in response to the notification. So for instance, you might get a notification saying some value has changed in your process, and that notification may not have enough information, so you might go and query the observed object for some more data. Think of that sequence of actions and think of how that could lead to deadlock under some policies that we've discussed and not lead to deadlock under other policies. Okay. So here's the situation which we finally got to. So we have a user thread in the client or the caller. We don't know what's the client and what's the server here. And we have, let's assume, one system thread, a pool with exactly one thread to invoke remote methods. Okay, so T1, the user thread, and let's go and use the observer pattern, which is something we know already, but this can, we just need multi-way calls here. It does a write to an observable. Okay, that write, when assume that caller blocks until remote call completes. Okay, this is what happens in RMI, and this is what you might expect naturally, because in local procedure call, the caller waits for the callee to finish before the caller proceeds. Okay, so if you want to have local semantics translate to remote semantics, that's what you would do, and that's what RMI does, even though I never exactly said so, because not all systems have to do that. Okay, that then invokes the notify method in the RPC caller system thread in the client. Okay, so we have two blockings. T1 is blocked on RPC caller in the server. RPC caller in the server is blocked on RPC caller in the client. Okay, or the callee process. And it's not a cyclic dependency because we have three threads, and we don't have a cycle going back to T1. Okay, so to make a cycle, we'll just go and say, okay, it did not get enough information in the notify. Maybe the notify took no argument, so it now makes a read call back to the original to the server. Okay, or the calling the process that has the server object, and now there is no system thread to execute this. Okay, so if there's only one RPC caller worker thread, read will not be processed until notify returns, which will not return until read is processed and returns. Okay, so you have now a deadlock situation. Okay. So I took the situation of there being only one thread in the pool. If I have multiple threads, will the problem get reduced, not reduced? And if you say it's reduced, does it get eliminated or just reduced? So that's our next question, now that you understand this. So what happens if I have two RPC caller threads, for instance? Can I get away from deadlocks, or can I get away from some deadlocks? Okay, so think about that now. Okay, so deadlock chance reduced. Yes, it does. Let's go and have the same situation as last time, but add another RPC caller thread. And so when the read call comes in, it can go to another thread and return, which will then unblock the first RPC caller. Okay, so we know that in this situation we don't have deadlock, so the problem has got reduced. Okay, which is what we talked about. And can it get eliminated? No, as Eugene mentioned, we can have as many user threads as there are caller threads, and they can make calls simultaneously. So here we have two threads making two different write calls, serviced by two, and thereby using both of the thread pool threads, and they then go and make calls back to the original process, which again make calls, and these calls cannot be serviced because there's no thread available. Okay, so by having a larger number of threads, you just reduce the chance, you don't eliminate it completely. Okay. if you have a static policy. If you have dynamic policy, then you can just introduce new threads and break the deadlock. Okay? And is that really, so you might say that, look, we shouldn't have any static policy at all if you want to avoid deadlocks. And I'm going to argue that maybe if you're worried about deadlocks, then it's your headache to solve it also. Because think of the observer pattern. In the observer pattern, we talked about the fact that and when an observable gets changed, it makes all these notify methods and all the observers, and any one of those observers can go and hang the whole observable. Right? Because these observers are in layers above the observable. Observable cannot make any guarantees about what the observers do. So we talked about actually the fact that the producer-consumer problem should not be that the observer pattern is a producer-consumer problem, and we should have multiple threads, consumers, and we should really have multiple threads involved there, not a single thread doing both the production and consumption. Okay, so even if there is only one thread, for instance, in the server process, we can eliminate deadlocks by just doing some programming ourselves, wherein we don't go and have the same thread. We just break up our program into multiple threads. Okay, and we saw how we could do that with the observable pattern. Okay, another way to break this problem is to say that we will not conform to local semantics when we do remote semantics. We will not make our procedure calls wait. Okay, so T1 does a write. It does not wait for the write to finish. It just says, oh, I assume it will work, and it just returns while the write is occurring in the server. And then it goes and makes a notify call, and it says, oh yeah, I've notified. I don't have to wait for the notify to finish, so I'll just return. And then it makes a read call, and there is an RPC caller thread available. Okay. Now the read call requires a value back. So the read call is really a function, and so we might make that block, but we could make the non-function calls or the procedure calls not block, and thereby reduce the chance of deadlocks. So you can still have deadlocks between function calls when function calls are involved, but at least the procedure calls don't introduce deadlock. Okay. So this is yet another way to overcome this problem. And when you have non-blocking procedure calls, then this whole idea of having checked versus non-checked exceptions is moot. It's not relevant. Okay. One reason to wait for a procedure to finish is to figure out whether there was an error. But if you're not waiting, then you can't use a normal exception mechanism to get errors. You might require errors to be sent through some other mechanism. Okay, so you can see in RMI they block, and the exceptions occur and they are checked. But we can try to break the rules in many ways and not block, and then when you don't block, then this whole checked versus non-checked exceptions doesn't make much sense. Okay. Okay, so we've seen that small versus large number of threads. We've seen the pros and cons, and one of the cons had to do with blocking issues and deadlocks. I'm going to argue that one is a special case. It sometimes makes sense to have exactly one thread in the thread pool. And it has to do with consistency. Okay? And consistency issues arise when there are multiple processes trying to change some data structure concurrently. And you want some guarantee as to what happened. You want to avoid you want the clients to all have a consistent view of what happened. And I'm going to argue that when that's the case, you want a small number of threads in the server, and you want exactly one thread, in fact. So think of that. Think of not only blocking versus non-blocking, utilization versus non-utilization, and how much concurrency you're using that is given to you by the processors, but also the consistency argument that sometimes a server is introduced to make a bunch of clients consistent. And in assignments 4 and above, that's exactly the problem you guys are facing. Assignment 1 to 3, you were trying to increase performance by having multiple threads and just multiple processes. Now you're given multiple processes, like a game like having a multi-user game, and you're trying to make sure that these games or these processes are all consistent with each other. And sometimes you need a server to make that consistency. And I'm saying when you have one thread in the server to process all incoming messages, consistency is more likely in certain situations. Okay? So think of that now. So that's the hint that concurrent changes made by different callers. And making number of threads 1 allows outgoing messages to follow the order of the incoming messages. Okay, so the server can go and mediate between the clients and serialize the actions. Okay, so once it serializes the actions, it can go and send the serialized actions to the clients, and the clients know in what order, so they can all agree on the same order of actions. So in the example we were talking about, where two clients have 2 copies of the file, and one writes 2 and the other writes 3, they both send the writes to the server. The server gets them in a certain order and echoes them back to the clients in the same order. So they will then go and decide on the same thing at least. Yes, one overrode the other, but it won't be the case that in one copy 2 overrode 3 and another copy 3 overrode 2. Okay, whichever message arrives at the server first is the one that gets overridden. Okay, the later one wins. And we can have policies where the earlier one wins. We can have many, many different approaches. Okay, so that's the advantage of having exactly one. Okay, so we have 5 minutes left, and I have a bunch of questions for you here, but I might just try to answer them directly because well, let's go through them. We can take time next time also. So I told you there are all these policies possible, and the question is, how do we determine what policy is being actually implemented? And we can read the documentation, but that's too boring, right? Who knows where that exists? We have the system in front of us. So if I was to tell you, figure out what the policy is, use RMI, what would you do? Okay, and I actually told my students last time, and they all had different answers. And so I decided to go and do the experiments myself this time. And this turned out to be a much harder problem than, well, the answers were much harder to decipher than I thought. And I actually don't have the exact answer in my head. I should really go and try to search on Google to see what exactly. I know what GIPC does because I implemented it, but I implemented it a long time ago, so actually I've forgotten what I did. So let's go and see, how could you go and determine what the policy is, given a black box system that you know nothing about. So think about that, because this is something that I think would be useful. This is a question that's useful to answer if you have debugging programs. So I think this would help you with the debugging also. So what kind of experiments could you run to figure out, to narrow down the policy? You may not be able to figure out the exact policy, but to narrow down the policy. You know, is it static? Is it dynamic? Is it a static number of, if it's static, the number of threads in the pool. So is it per call thread or a pool? If it's pool, is it static pool or dynamic pool? If it is static pool, is it one thread or multiple threads? I want to answer these questions. Okay, so try to imagine you want to answer any one of these questions, not all of these questions. What experiments might you do given and assuming you're in Java, to figure out, and you can write your server objects, right? You can write server objects that go and print out anything you want them to print out. Okay, you can make any kind of remote calls you want to. The calls, calls you make are in objects you've written. You can print out system data. Okay, you can imagine any, whatever system data you want to print out, from an operating system. Imagine that you can, except that you can't go and identify whether there's a thread. You don't have information about RMI, but you have information of the operating system. So anything that the operating system keeps about threads, you can print out. But you don't know which thread belongs to which pool, and that RMI is a black box, but the operating system is not a black box. And in Java, you can't print out a lot of information. So what might you print out or to figure out, to narrow down the policy? So what we can do is we can connect multiple calling processes and threads to a common call process. Multiple calling processes because we might want to know whether the thread pool is shared or not shared. Okay? And we can print the current thread in each remote call. Okay, now printing the current thread does not give you the exact information because printing the current thread will give you the toString, and who knows what the toString does. ToString could go and actually look at some values in the, it could change dynamically. But there's one thing you can do. There's something called the system identity hash code that identifies an object and it never changes for an object. Okay, think of that's the closest to an object address or pointer that you can imagine. So you can print the threads and think about using the thread printings to figure out what the policy is. Okay. And we'll go and see how we can use this, how I've used this stuff, this mechanism to actually figure out, to narrow down the policy. Okay, so we'll do that next time, and then next time we'll also probably start on MapReduce discussion. And we can also do the following. I found that you can also print the number of threads. In each call, you can print out the total number of threads that the system has created, that the process has. Okay, so if I know the total number of threads, I can see whether the total number of threads changes dynamically for each call or between calls. The fact that it didn't change, may not tell you much because it may change later. It may, you may just not have exercised the system enough. The fact that it changed may also not be enough because the number of threads could change for other reasons that have nothing to do with the pool that you're using. So it's noisy data. That's why I'm saying we can try to use these data to narrow down the policy, though we may not be able to get the exact policy. Okay, so if you guys have time, why don't you guys maybe try to run these experiments, or I'll be very curious whether you guys can find documentation on this also, and then you can tell me the exact policy. I didn't try to search for the documentation, honestly. I just thought this was more interesting, and I wanted to go through the process with you. Okay, but try to figure out what RMI does with how it allocates threads to your calls. Okay. So the issue we looked at last time was the was how remote calls are serviced by threads in the callee process. Okay, so there's the caller process that invokes the call, and that callee process invokes the call in the thread used to invoke the call. That's a user thread. Okay, but then the call gets transferred to the callee process, and that transfer is magic. So the question is, what threads, if any, are executing those calls there? Okay, where is the work being really done? Who's doing the work? Okay, and we saw that there were many policies. We could create in the callee process a thread per call, or we might have a thread pool where the same thread is reused multiple times for different calls. We can have if we're going to have a thread pool, we can have a static number of threads in the pool, or we can change the size dynamically. Given that there might be multiple calling processes for a callee process, we could have the pool be shared among all the calling processes, or we might have per connection pool. And if you're going to have a static pool, the question is, what is the pool size? Okay, so there are pros and cons, and I mentioned last time that these are concerns. These are concerns that may be relevant to also the programmer. Okay, as an implementer, you need to figure out how to handle these concerns. But as a programmer, you also would like to know something about these policies, because we saw certain policies could lead to deadlocks while others don't. Okay. So and then the question becomes, how do you figure out what the policy is? And you can try to figure out the manual if it's written. But we can also try to experimentally find out what the policy is. Okay, and so in general, when you do distributed programming, you tend to run experiments for performance and other reasons, consistency reasons. So it's good to sort of see how we might go and structure an experiment. Okay, and what data can we use. And so we're going to sort of try to together figure out what the policy is in RMI, which is one system for creating remote method invocations, and then GIPC, which is the system I created. And we saw the various means we have at our disposal. I said you can't go and just query RMI and ask it, what is your policy? And get an answer back. So what you need to do is figure out, and I said what you can do is use primitives that the operating system provides, and these are the lower level. So we can go and create an experiment where we have multiple calling processes for one called process. So this might help us figure out whether policies are per connection or not. And we can try to figure out for each call what thread is executing it. We can just print in each call the thread toString. Okay, and so the toString of an object gives you an idea of the identity of the object, but the toString can vary, can change as the object state changes. So there's another mechanism that you guys probably don't know about, which is the system identity hash code. So there is the hash code used when you go and put the object in a hash table, and that can change based on the contents of the object. Okay, but the system identity hash code doesn't. So that's another thing we can try to use if we need to. Okay, and there's also a way to figure out, at least in Java, the number of threads in the system, in the process. Okay, you can go and say, tell me how many stacks there are, and each stack corresponds to a thread. Okay, so we have these means at our disposal if we want to go and figure out what the policy is. So, like I said, we need to go and set up an experiment, and we're going to narrow the policy down. We won't exactly know, just because of a few test runs, we can't for sure guarantee that we figure out the right policy, but we can try to narrow it down. So the experiment that I first ran involved two calling processes, each with one thread in it, and we have already implemented a counter, so they're both threads are going and calling the increment method in the calling process. And this is observer pattern here. We have an observer pattern here. So the called process goes and invokes a property change in all the in the calling processes. Okay, I'm not saying server or client because it can go either way. Okay, that has to do with awareness. But usually the call process, the first call goes to the server, and then the callbacks occur in the client. Okay, and to distinguish between the two processes, I'm going to have one process give positive increments, and one process feed negative increments. Okay, so we'll know from the console output in the server which process was invoked increment. Okay, so the second process is going to give negative increments. So that's my experiment. I have appropriate print statements in the server in the called process, and I'm showing you three traces. Okay, and I've colored them based on whether the traces contain positive increment changes or negative increment changes. And we know that negative increment changes occur in one process and the positive in the other process. Okay? So the green ones are process 1, let's say, and the calling process, and the orange one is process 2. So if you notice here, you've seen such traces in your programs. And these traces print out the threads. And so you see here, RMI, TCP connection, blah, 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 the address. So that is the thread toString that is printed out. Okay, and it has the host of the calling process, and it tells you, it's got the term RMI TCP connection to indicate that this happens. This thread is related to a TCP connection. For those of you who run networking, you know that's the underlying connection, and it's got this suffix 2 here. And if you notice for the orange process, the suffix is 3. Okay. And then you notice that the suffix goes to 4 for the green process for the third call. Okay, so that's what we see here. And the question is, how might you be? What might this be telling you about the choices we have for the policy? Okay, So based just on this data, it's not full data, what are some hypotheses about the policy? Okay. So what are some hypotheses that are consistent with this data? Okay. So that's my first question. Okay, so since the threads, two strings are different for each call, thread per call is consistent with this. Okay. And we also, as Yuji mentioned, that we don't have enough information, and as David hinted, David thinks it might be a pool. Okay, it just might be different threads in the same pool, in a pool being used to service, but certainly this doesn't discount thread per call. Okay, so let's go and assume for the moment thread per call. So let's see some more data. Okay. Now I have some more data here, and what do I see here? I'm also printing out now the number of threads in each call. Okay, so I go and see that it was thread number 2. Okay, and in that, and while that call was before the call was serviced, or after, I think it's right after I put the trace statements, I print out the total number of threads as 14. Another call comes in, same thread ID, and the number of threads is still 14. Okay, and a call from the other process, thread ID is 3, and the number of threads is still 14. Okay, so the question is, what kind of policy might be maybe consistent with this? Okay, there may be multiple, and so that's this new data. So if, again, hypothesis, I'm always saying this is a hypothesis, assuming a constant mapping between toString and thread, we see that the same thread can service different calls from the same but not different processes. Okay, and so we see that it's a pool then, and it may be per connection because we haven't seen the same thread being used for calls from different processes. Okay, and it seems too much of a coincidence that it's always 14. Okay, 1, 2, 3. So the chances are very high that we have kept the number of threads constant, and it's not just it's not that there's always this a call occurring and it remains 14. Okay, so it could be per connection. Now we've got some more data. We've got 3 here, and we've got num threads 14, and we've got 34 next. So Yuji thought that these thread IDs are reused, but we've gone all the way down to 34. Okay, and the number of threads is different now. It's 13. Okay, so what conclusions could we draw from this? So what we see here is that the number of threads dynamically changes, and that can happen for 2 reasons. It could be that some other activity occurred in the process that changed the number of threads, or it could be because the thread pool changed. Okay, this is noisy data. We don't quite know why the number of threads is changing. It could be that we always have that one active call, and that's why it's 14. So we really don't know. But we have gone to number 34, so maybe it's dynamic. Okay. What the exact policy is not as important as us being able to think about the possibilities and understand the difference between static and dynamic, because these differences are becoming concrete through these examples. So let's go and test, whether the mapping between thread object and thread toString truly changes or not. Okay, so let's go and print out, in the next slide, we'll print out the system identity hash code. Okay, so we can say it's dynamic and per connection right now, and that what we see here is not inconsistent with. So now I'm printing out the hash code, system identity hash code, and I had to try many increments before I got what I wanted to see. Okay, so see now what's going on here. We have the orange thread and the green thread. One is number 3, and it's got a system identity code of this of this particular number, and here is another toString, different calling process, and the same identity code. Okay. So what conclusion can we draw from this? So the thread toString of a thread with a unique changes depending on the connection. Okay, so this mapping is not constant as we were thinking it would be. Okay, that, and I honestly, when I was trying to figure this out, I thought it would remain constant till I saw some till I saw behavior that I just didn't, believe would occur, should occur, and finally I was, like I said, I was able to get the data I needed. So so we do see that the same thread can service calls of different clients. Okay. So we can decide that the pool is shared, okay, which is what we would expect. And it may be static or dynamic. We don't know from the thread count. That's noisy data. Okay, it could be static or dynamic. The 14 could have gone to 13 because of some other thread having been created by the system that's unrelated to RMI, or it could be because the pool is dynamic. Okay. Okay, so we know that we have so in that experiment we showed that there were two threads with the same system identity code. I didn't show you data that showed that there were typically threads with different system identity code. So from that we can say that it's not just one thread that's servicing all calls. Okay, and if it's not one thread that's servicing two calls, hopefully we shouldn't have deadlocks. Okay, we said that we can have deadlocks with two-way callbacks if we have only one thread servicing all calls. So let's just verify that that's indeed the case, and that will also help us narrow the policy. So now I'm going to have two threads again doing positive increments, and again there's going to be a property change callback in the calling process, and we're going to have another call back to the call process. Okay, this is what in our previous lecture we saw cause deadlocks. Okay, if there was only one process, only one thread servicing all calls, we saw that there was deadlocks with this arrangement. So now that we believe that there's more than one thread and there's a thread pool, even though it's shared, hopefully we won't get a deadlock with just one callback, one increment at one time. Okay. So here's a long trace, and it confirms what I said, but let's just see how. So we call increment with 1. Okay, that goes and invokes a callback. So I'm tracing the start of the callback, okay, to a proxy object. So we see here the proxy object printed out, and this increment has not yet returned. But what we see is that a get value is called. Before the increment or the callback terminate, a get value is called because of the initial calling process making that call. And the first thread is waiting, okay? So this get value must be invoked by another thread, and we do see that thread's TCP connection is 5, okay? And I'm not printing out the system identity code here because I did that at the end of my experiments, and also because it would just make it even longer, okay? But we can be pretty sure that these are two different threads because the first thread has not yet printed out saying that it's finished the callback, okay? So the get value returns, that unblocks the first call process, and now the callback terminates. The first callback terminates after the increment. There are two calling processes, so another callback is going to be called, okay, and that results in yet another get value invoked by a different thread than the one that's waiting. And here we see that the callback now ends. So we did not get deadlock. So what we see here is that a get value is called by some thread 2, okay, before callback in thread 1 finishes. Okay, so before callback 1 or 2, I don't know why I say callback 2 here. Before the first callback in thread 1 finishes, a get value is called in thread 2. Okay, so we see that. Okay, and because we see that before a lot of actions occur between before callback printout and after callback printout, we can assume that the callback actually did block. Okay, otherwise the before and after would occur in succession, and they didn't. So this seems to indicate that the calls are blocking. Okay, so that's an issue that I said could be handled in more than one way. Okay, so to conclude that there is, and I should really make, like I said before, get value in thread 2 call before either callback 2 or callback 1 in thread 1 finish. Okay, so this is what I mean here. Had there been only had the calls been non-blocking, we would get callback 1, callback 2, then get value 1, get value 2. We'll see that later. Okay, because the callback 1 would just not block, so and then callback 2 would be invoked, and then later when the message arrives at the first calling process, it will go and call get value, and so it would occur in that order. So this is not what happened. So we can decide that there was really blocking. Okay. So let's go and see a different policy now. Again, we'll do first one-way callback, and we see here that the green process, it has the thread two-string asynchronous received call invoker, and then we see that for the other process also we see the same name, and assuming that two strings and thread objects have one-to-one mapping, the same thread is being used again and again, and this is a system I've implemented, so I can guarantee you that the mapping doesn't change. Okay, so there's only one thread. So same thread services all calls. Okay, though I want to indicate that this to you, that at some point you will do an assignment where this is going to become important, and so there's a factory that decides what really happens. Okay, so given that there's more than one useful policy, I've got a factory, and you have to make sure that the factory does the right thing. Okay, so this is just what the factory I'm using does. So if I have only one thread here, what happens with these two-way callbacks? Okay, and let's see what happens. So my animation is a bit off here. So this particular thread is called with incrementer 1. It goes and says before callback, and immediately after that it says after callback. Not like what happened in RMI. The call doesn't block. Okay, so it's notifying one process. The message goes across over the network. It doesn't wait for the get value to come from that process. It doesn't wait for anything. And then it goes and it invokes this call on this proxy. And then we see before callback and after callback for the second process. And then the get values come in, first from the one caller and then from the other caller. Okay, so you see how these things are mixed in different ways. Okay, and that's because there's no blocking here. And because there's no blocking here, we don't get deadlocks, even though there's only one thread executing all remote calls. Okay. So get value in thread. Okay, so this needs rewriting. So there's only one thread. I shouldn't have thread 1 and thread 2. So the get value 1, the first get value occurs after both callbacks finish. That's what I'm trying to say. Okay. And so get value has hopefully worked correctly, and get value needs a value, so it better be blocking. So what really happens is that the procedure calls, that ones that don't return values, are not blocking, and function calls block. Okay? One of your assignments will go and make the procedure calls also block. Okay? And so that will be your little exercise in understanding how remote procedure calls work. And so that's where we'll have to worry about blocking, about deadlocks, and make sure that we program at a higher level in such a way that we don't get deadlock. Okay, so let me end this discussion on RPC, RMI. We divided this discussion into sort of the basic concepts and the advanced concept. Basic concepts allow you to implement your assignments. And the advanced concepts, we looked at, what does the proxy state contain? And we saw some of the components of that state. We saw that if you have checked remote exceptions, then we have to go and execute object methods locally. But if you have unchecked remote exceptions, then as in GIPC, you can invoke object methods remotely. Okay? And allows remote classes and callers to be distribution unaware. And so that, that's another implication. But just because you can execute something remotely doesn't mean it's a good idea to do so. I'm convinced that you don't want toString to be executed remotely, because when you debug, your debugger just hang. So if you're designing a system, maybe the equals operation should be executed remotely, but I'm not sure any other operation should be. Okay. So then we also saw, what are various policies for creating threads at the called site, called process. And we saw the pros and cons of having a new thread for each call. We certainly won't get deadlocks in that scheme. And we can have static versus dynamic. And if you're going to have static, we can have small or large pools. And then we can have the pool size be 1 or greater than 1. And if it's 1, we saw that we can have certain consistency guarantees that we might not have otherwise. Okay. And then the pools can be per client or shared. And that's fairness versus generalization. And if you're going to use local call constructs to return values, then we need blocking calls, blocking function calls. And if we are blasé about exceptions or use some other mechanism to go and get errors, then we don't need remote procedure calls to block. And so in RMI, the calls block. In GIPC, they don't. But there's also a Google RPC mechanism that I've used, and there also is asynchronous. Okay? So that makes sense. And an implication, if you don't have blocking, not only will certain kinds of code run faster because you're not waiting, but you will not wait forever and not have deadlocks because of two-way callback.